Hello, this is a very important AP problem that I got wrong. So let's read it. In scenarios 1 and 2, block Z hangs from a string. And then the differences here are that here it's a string connecting X, Y. Here it's a spring. And then when both systems are released from rest, what is the acceleration as the hanging block as a function of time? Well, what I did wrong myself was I assumed that the external force is the same in both systems. Now you can tell because if we treat these as systems, the only force external is gravity because friction is negligible. So I quickly jumped into the conclusion that deduces the fact that the acceleration of the system is equal to the acceleration of each cart. Now this is only true for scenario 1, which is where all the strings are ideal. So ideal strings. So what we mean by ideal strings is they don't stretch, so they keep the distance between X and Y constant, and then they can also pull on each instantaneously. And the tension everywhere is the same, given the same portion of the string. But this isn't necessarily true for scenario 2, so we will have to think about scenario 2 more. So we have a spring, right? Spring. So when we suggest a spring, what do we think of? Well, we think of Hooke's law, right? F equals kx. Negative kx restoring force. The important thing to note is here, even though these two acceleration of systems are the same, is this acceleration of the system is not necessarily equivalent to the acceleration of each cart. Now, why is that? Well, first of all, when t is basically at 0, x does nothing because this string is relaxed and x has no force acting on it, so it's just y and z. But as y displaces, that causes the string to stretch out, right? And once that string stretches out, that's going to exert a force on x to pull it this way, but it's also in turn going to pull y back, right? So all three blocks, actually these two are going to move at different rates, right? Different accelerations, and therefore we cannot simply say that acceleration of the system is equal to acceleration of the carts. So the restoring force does depend on time here, because it's going to oscillate between stretched out and relaxed length, right? Because when y moves this way and x barely moves, it's going to stretch out, and then as a result of that, x is going to move forward, and then the string is going to shrink back into its basically original equilibrium position. So what that does is that influences the tension in here. Because let's say y is getting pulled back. Now, because y and z still accelerate at the same because of this ideal string, given the same time, that would mean, for example, if they're still accelerating to the right and down, then this tension is equal to this tension, and then gravity is like this, right? But if y isn't getting pulled in as much in the oscillation of the spring, then tension doesn't have to pull that much and fight against the spring force. And then in that period, z accelerates faster. So it's just an oscillation, basically. And it is not that simple to conclude that A1t and A2t are always equivalent. So by that logic, we have to say that A1t is not exactly equal to A2t, and this is the best answer choice in this scenario. Thank you for watching.